Both of these robots are trying to deliver a package. This one costs $75,000 and this one only $2,000. Same job, 37 times the price difference. 2 motors, 12 motors. And those 10 extra motors, that's not just a parts list difference. That's the entire economic battles of robotics right now. Because here's the question. Every robotics company and every builder has to answer. Is climbing a curve worth 600% increase in the manufacturing cost? By the end of this video, you will understand why Amazon chose wheels, why search and rescue teams needs legs, and why tanks use tracks, and why the ultimate home robot still doesn't exist. The engineering trade-offs between cost, terrain, capability, and energy efficiency. Not what looks cool in a viral video, the actual manufacturing economics. I am Vakar Curious and I decode the architecture of AI-based devices. Let's break down the terrain cost war. Before we get into the cost war, you need to understand the fundamental physics of how systems work. Because wheels, legs, and tracks aren't just different designs. They are solving completely different problems. Let's start with the wheel. This is one of humanity's most perfect mechanical inventions. Watch how little energy that took. One push, continuous motion. A wheel converts rotational motion into linear motion with almost zero energy loss as long as the surface is smooth and flat. That is what we call static stability. It doesn't need to think about balance, it just stays upright. I can turn this off right now and it won't fall over. Like a table with 4 legs, gravity keeps it balanced automatically. No computer needed, no calculations. As long as the center of gravity, the balance point stays inside the support base, physics does all the work. Energy-wise, wheels are insanely efficient on flat ground. A wheeled robot might use 10 to 20 joules to move 1 meter. Think of joules like miles per gallon of a robot energy. Lower number means the robot goes farther on the same battery. That's why your Roomba runs for 8 to 12 hours on a single charge. But now, watch what happens on rough terrain. The wheels sink in. The motor is working 5 to 10 times harder for the same distance. And this, a 4-inch curve, is an impassable wall. The wheel physically cannot lift the robot's center of mass, its balance point, over an obstacle taller than half the wheel's height. So wheels are perfect for the world humans have paved. Now legs. Legs exist in nature for one reason. Unstructured terrain, rocks, mud, grass, stairs, surfaces where a wheel would get stuck or get stopped. Legs work by choosing exactly where to step. They adapt to the terrain instead of requiring the terrain to adapt them. But here's the catch. Unlike wheels, legs need dynamic stability. That means they are only balanced when they are actively moving and adjusting. Think of riding a bike. While you are moving, your balance is easy. The moment you stop, you fall over. Legs work the same way. Every millisecond, literally 1,000 times per second, the robot's computer is calculating. Where is my balance point? Which feet are touching the ground? Am I tipping forward or backward? What do I need to do right now not to fall? Each joint uses what's called a servo motor. Unlike a regular motor that just spins like a fan, a servo motor is smart. It knows exactly what angle it's at and it can push with precise force. Feel that resistance? The servo is fighting me, trying to hold this position. So when the robot starts to tip forward, the front leg servos push harder. The back legs adjust their angle. It's constantly catching itself from falling. This is why legged robot always looks like they are dancing. Because they are. They are doing 1,000 tiny corrections per second just to stay upright. And that dance requires massive computational power. A wheeled robot dedicates maybe 5 to 10% of its computer brain to movement. A legged robot, 40 to 60% just not to fall over. And here's where the cost explodes. Each leg has 3 joints, hip, knee and ankle. Each joint needs one servo motor, one position sensor, sometimes a force sensor to detect how hard it's pushing. 4 leg times 3 joints equals 12 servo motors. All need power, control signals and perfect real-time coordination. And then there's the third option, tracks. Tracks spread the robot's weight across a huge surface area. Instead of 4 small wheels touching the ground, you have an entire belt distributing the load. This is critical for soft terrain like mud, sand, snow, Places where wheels would just sink and spin uselessly and where legs would struggle to find solid ground. Tracks also let you do something most wheeled vehicles can't. Spin in place. Stop one track, run the other, instant pivot turn. But tracks have a fatal weakness. If a track breaks or gets knocked off its wheels, the entire vehicle is dead in water. A wheeled vehicle can lose one or two wheels and limp to home. A legged robot can lose one leg and hop. A tracked vehicle with a broken track, completely stuck. So here's the fundamental trade-off. Flat, smooth surfaces, wheels win. Cheap, efficient and simple. Mud, sand, heavy loads, tracks win. More expensive, louder but unstoppable on rough ground. Stairs, rubble, extreme obstacles, legs win. Very expensive, very complex but can go where nothing else can. The question isn't which is better, it's which terrain are you willing to pay for. Now let's talk about the two camps fighting this war and the engineering bets they are making. Philosophy number 1. We have already paved 99% of the world. Let's build robots for that reality. This is Starship Technologies. Amazon Scout. Every last mile delivery company uses wheeled rovers. They're thinking most delivery destinations are accessible via sidewalks. Sidewalks have curb cuts, those wheelchair ramps at intersections. If it's accessible to human wheelchairs, it's accessible to our robots. So instead of spending 50,000 on a robot that can climb stairs, spend 2,000 on a sidewalk only robot and deploy 25 of them for the same budget. This isn't about technology. It's about fleet economics. How many robots can you deploy for your money? Let's look at the bill of materials. Basically, the shopping list of every part you need to build this robot. Basic delivery rover. 2 to 4 drive motors, $50 to $80. Controllers to manage those motors, $30. Battery pack, $200. Sensors, cameras to see, ultrasonics to detect obstacles, $150. Plastic chassis and wheels, $200. Small computer for navigation, $150. Total parts cost $800 to $900. Add assembly labor, software development, company profit. You retail this thing at $2,000 to $3,000. Now compare that to a legged platform. A quadruped robot parts list. 12 high performance servo motors at $150 to $300 each. $1,800 to $3,600 just in motors. Position sensors for each joint, $600. Powerful computer to run balance calculations, $500. Bigger battery because legs drain power faster, $400. Balance sensors, 4 sensors, cameras, $500. Precision machined metal frame, $800. Total parts, $4,600 to $6,400. Retail price after markup, $15,000 to $75,000 depending on how advanced it is. 10 times the cost. Minimum. And that's before we talk about the software. Wheeled robot software, obstacle avoidance, path planning, knowing where you are on a map, maybe 50,000 lines of code. Legged robot software, gait generation. That's the pattern of how legs move, like a walk versus a trot. Balance control, terrain adaptation, real-time calculations for each leg, easily 200,000 plus lines of code. So the wheeled camp's philosophy is simple. We are not solving the hard problems, we are avoiding them. And it's working. Starship has completed over 6 million autonomous deliveries across multiple countries. Their robots operate 24/7 at massive scale. They picked easy mode terrain and build a business around it. But there's a world those robots can't touch. Philosophy number 2. The world wasn't designed for robots. Build robots that adapt to the world as it exists. This is Boston Dynamics, Unitree, Anybotics, the legged robot companies. Their argument, there are entire environments that wheeled robots cannot simply access. Power plants with stairs, construction sites with debris everywhere, disaster zone with collapsed structures, homes with multiple floors. And if you are selling to industries where the robot replaces humans doing dangerous works, inspecting high voltage electrical equipment, entering contaminated zones, searching through rubble for survivors, cost becomes relative. A human inspector costs $60 to $120 per hour, plus health insurance, workers' compensation, safety gear, liability if they got hurt. A $75,000 spot robot working 2,000 hours per year for 5 years, that breaks down to $7.5 per hour, zero injury risk. So for industrial inspection, oil and gas, mining construction, legged robots make economic sense. But here's what Boston Dynamics doesn't put in their marketing. These videos go viral every time. Millions of views, incredible engineering, Atlas doing backflips, spot dancing to Uptown Funk. And Boston Dynamics has never made a profit. 30 plus years building the most advanced robots on the planet, and they have never turned a profit. Hyundai bought them in 2021 for $1.1 billion. Not because Boston Dynamics had a money-making business, but because Hyundai wanted the research pipeline and the engineering talent. Those viral videos, that's what I call R&D theater, research and development theater. It's impressive. It pushes the boundaries of what's possible. But the real money in robotics right now, it's boring warehouse bots with wheels moving Amazon packages. Because engineering excellence doesn't automatically equals business success. Tracks sit in the middle. They are the heavy-duty choice when you need to carry serious weight over rough ground. Mud, sand, snow. Tracks distribute weight and keep moving when wheels would just spin. And then there are hybrid systems. Handle has wheels at the end of legs. It can roll like a wheeled robot on flat ground, but use the legs for balance, jumping over obstacles and going up upstairs. There are also systems with wheels that transform into leg-like shapes or tracks with flexible suspension. These are mechanically fascinating, but they inherit the cost problems from legs. You still need all those expensive servo motors, and they haven't proven themselves at commercial scale yet. Right now, hybrids are mostly in research phase. Let's look at where each approach is actually winning in the real world. Last mile delivery, getting packages from a warehouse to your door, Starship operates in over 80 cities globally. Millions of packages delivered, college campuses, suburban neighborhoods, business districts. Cost per delivery with Starship is $1 to $2 once you have got the fleet running. Human courier, $5 to $8 per delivery. Trying to do this with a $75,000 legged robot, the math doesn't work. You would never break even. Notice what Starship did strategically. They didn't solve the stair problem. They picked markets where stairs don't matter. College campuses, mostly flat, designed for wheelchair access. Suburban neighborhoods, curb cuts at every corner. Business parks, built to code with ramps everywhere. They didn't build robots for the world. They picked the 85% of the world that fits their robots. This is what I mean by infrastructure surrender. They are not saying we are not solving the hard 15%. We are ignoring it and focusing on easy 85%. And you know what? That's where the money is. Now, why am I showing you all this business strategy? Because if you are a builder deciding what to prototype or a product manager deciding what to fund, this cost difference is what kills projects. A 10 times price gap means you need to prove 10 times better results, and legs don't deliver that for most use cases. Now let's look at where legs actually win. Industrial inspection. Offshore oil rigs, electrical substations, mines, factories. These places were built for humans, not robots. Stairs everywhere, metal catwalks, uneven grating. Sports customers aren't regular people. They are companies like BP, energy utilities, construction firms doing infrastructure work. Thermal imaging cameras checking for hotspot on electrical transformers. Gas sensors detecting methane leaks, radiation monitoring in areas humans shouldn't go, 3D mapping of dangerous construction zones. Jobs that are repetitive, dangerous, and really expensive when humans do them. And the robots aren't making decisions on their own. They are mobile sensor platforms. A human operator back in a safe control room sends Spot into the hazard zone, looks at the sensor data and makes the actual decisions. Boston Dynamics has sold or leased a few thousand Spots since 2020. Compare that to Amazon deploying hundreds of thousands of wheeled warehouse robots. Legs win in specialized niches where the terrain is hostile and the return on investment justifies the premium cost. But they are not winning the volume game. And tracks, they dominate in military operations and heavy-duty disaster response. Search and rescue after earthquakes, bomb disposal units, military logistics in war zones where roads don't exist anymore. Tracks give you reliability in the absolute worst conditions. Mud that would stop wheels dead. Rubble fields that would confuse a legged robot and balance system. And they can carry serious weight, hundreds of pounds of equipment, sensors, supplies, something legged robots really struggle with. Because every extra pound multiplies the load on all 12 servo motors. The trade-off, tracks are loud. You can hear them coming from far away. They are mechanically complex to maintain. If one breaks in the field, you are completely stuck. But when you need to get a 500-pound robot through a disaster zone carrying rescue equipments, tracks are often the only option that works. And then there's a problem nobody solved yet, the home. Everyone wants the ultimate home robot, something that can fetch items from different rooms, help elderly people, carry laundry between floors, and clean the whole house. Right now, the only commercially successful home robot is the vacuum. Wheels, single floor only. Why? Because the moment you need to go upstairs, you need legs, and the legs blow up the cost. A Roomba, $300 to $800. A home robot with legs that could climb stairs, $15,000 minimum. No regular consumer is paying $15,000 for a robot to carry laundry upstairs. Not yet, anyway. So the ultimate home robot stays science fiction until someone figures out how to make leg robots cheap enough for consumer products. Which brings us to the real question. Will that ever happen? Let's break down exactly why legged robots cost so much and whether that can change. This is a $15 hobby servo. Works great for a toy robot. This is a $200 industrial servo for a real quadruped robot. Why does this cost 13 times more? First, torque, rotational force. The industrial servo has to move a 60-pound robot, not a 2-pound toy. That requires much stronger magnets, precision bearings, hardened metal, gears that won't strip under load. Second, precision. It needs to hit exact angles with a fraction of a degree for balance control. Cheap servos wobble and drift. Third, force, sensing. High-end servos can detect how hard they are pushing, so the robot doesn't break itself or your furniture when it bumps into things. Fourth, response, speed. Balance calculations happen hundreds of times per second. The servo has to move that fast and that accurately. And remember, you need 12 of these, plus the electronic controllers to drive them, plus the powerful computer running the balance algorithms in real time. Manufacturing complexity multiplies everything. Wheels, injection molded plastic, mass produced by the millions, snapped together in minutes. Legs, precision machined metal joints, custom servo motors. Every single joint has to be individually calibrated, tuned by hand, or the robot will walk crooked or fall over. And every servo motor is a potential breaking point. A wheeled robot has 2 to 4 motors total. If one fails, it can usually limp home. A quadruped has 12 motors. If one leg servo fails while the robot is walking, face plant, total mobility failure. So the 10x cost rule isn't just about buying more motors. It's about multiplication of everything. 12 motors instead of 2 times precision manufacturing requirement times individual calibration labor times supply chain complexity. Specialized parts are harder to source times the need for redundancy and robust failure handling. Every leg you add isn't just 3 motors. It's 3 motors times the entire engineering ecosystem required to make those motors work in perfect coordination. Now let's talk about something people don't think about. Energy consumption. Wheeled robot 8 to 12 hours of runtime. Legged robot 2 to 4 hours. Why such a huge difference? On flat, smooth ground, a wheeled robot uses about 10 to 20 joules, units of energy, to move 1 meter. A legged robot on the same flat ground, 50 to 100 joules per meter, 5 times more energy for the same distance. Why? Because legs aren't just moving forward, they are lifting the robot's entire body weight up and down with every single step. Watch the body closely. See how it rises and falls slightly with each stride. That up and down motion costs energy. Wheels don't have that problem. They roll at a constant height. And that's because we account for the computer. The computer constantly running balance calculations, 20 to 40 watts all the time. The balance sensors, force sensors, motor controllers, all drawing power continuously just to keep the robot from falling. A wheeled robot's simple navigation computer, 5 to 10 watts. So yes, in theory, legs can be more efficient on really rough terrain like deep mud or a boulder field where wheels would get stuck and waste tons of energy spinning uselessly. But in practice, for most real-world terrain, the computational overhead and the mechanical energy cost eat up any efficiency advantage. Alright,
Here's your practical decision framework. If you're building a robot for warehouses, roads, sidewalks, any known flat environment, use wheels. This is the right answer. Don't overthink it. Industrial facilities, disaster zones, places with stairs, rubbles, and hazards, use legs. If you're replacing a dangerous human labor at $100 per hour, a $75,000 robot pays for itself. If you're delivering pizza, it doesn't. Construction sites, military operations, heavy loads in muds, tracks are your answer. When you need weight distribution and don't care about noise, tracks are the answer. Homes, consumer products, mixed everyday terrain, wait. The technology isn't economically viable yet for mass market. The robot that wins in the market isn't the most impressive one. It's the one whose terrain capability perfectly matches its cost structure. Remember when we talked about LiDAR versus cameras in self-driving cars? Tesla's bet on cheaper cameras to hit consumer pricing. Starship is making the exact same bet with wheels over legs. Are they wrong? Look at the deployment numbers. Starship, 6 million deliveries. Boston Dynamics, a few thousand robots sold. The market has spoken. But here's what's coming that might change everything. New motor technologies are dropping costs by using smarter mechanical designs that don't require as much precision manufacturing. AI optimized movement patterns are reducing how much computer power you use for balance. In 5 to 10 years, we might see capable legged robots hit $5,000 instead of $50,000. At that price point, the whole equation changes. Stairs stop being a deal breaker for consumer products. The home robot becomes economically possible. But until then, remember this fundamental truth. Nature uses legs because nature didn't build paved roads. We did. And the robots winning right now are the ones optimized for the world we built, not the world that looks cool in viral videos. Alright, if you want the full decision framework, a flowchart for choosing wheels, legs or tracks based on your terrain, budget and energy requirements, I put together a free PDF. Link in the description. First link, grab it now. And subscribe if you're here for the manufacturing economics and the architecture breakdowns that nobody else shows. In the next video, I calculated the exact moment humanoid robots become cheaper than human workers. Thanks for watching. I'll see you in the next one. Stay curious.